Hey there, this is Lecture 6. We're going to talk about the history and discovery of radioactivity and why it's such an interesting topic that sort of demands that you understand a bit more of the nature of reality, I guess, the nature of matter. And the story of radioactivity really goes back to Austrian silver mines, where they were finding, in association with silver, what turned out to be uranium ores. Now, a fellow named Henri Becquerel was studying these uranium ores, uranium salts, and he had them in his lab, and they seemed to be emitting some sort of energy or light, or he didn't really know. He thought they were being sort of charged up in the sun, like glow in the dark, whatever. And the way he was testing this was taking these uranium salts. Uranium's an element, by the way, so it can form minerals, like Uraninite. That's a uranium-based mineral that we know now. Anyway, so he takes this uranium salt, which is just a compound of uranium, and places it near a photographic plate. And he found that it sort of develops on the plate. He could place something blocking the salts right in front, and the shape would come up, like the Maltese cross, for example. That was the classic one. But what was most interesting was found out by accident. He left all his gear in his desk for the weekend or whatever, where it was completely dark. He had his photographic plate, just this material, this uranium salt, just placed on top. Just he'd put it away. Came back, and after having been in complete darkness, this photographic plate was exposed. So light hadn't gotten to it. What was making the plate react as if it had light shone upon it? It was obviously something in this uranium that was doing it, but he didn't really know what. Marie Curie, Madame Curie, who many people will have heard of, took this sort of discovery and ran with it. She studied what was coming out of these uranium ores. And she didn't know, but she could actually differentiate different types of radiation. And because she didn't really know what they were, she called them alpha decay, beta decay, and gamma rays. Just like as if they were called XYZ types of radiation. She just noticed that they produced different effects. She discovered other radioactive elements, because what she found is when she isolated uranium the element from uranium ore, uranium the element was actually less radioactive than the original ore. So obviously there was something else radioactive in the rocks coming out of this Austrian mine. And from that sort of implication, she found polonium, named after Poland, her homeland, and also radium, which, quite a fantastic woman actually. She went on to win 2 Nobel Prizes, the first ever to do that, and first person ever to do that. And her research into radium led to the idea that cancer might be able to be treated with radioactive substances like radium, which is a pretty big thing. So another thing she did was mobile X-ray units in World War I, because her research into gamma rays, which are a bit similar to X-rays, kind of pushed her in that direction. So Marie Curie studied radioactivity quite in depth, but she never really got to what radioactivity is, other than categorizing these new elements and also categorizing types of radiation. Some radiation can travel through only a few inches of air, and some can go through, say, a sheet of paper, and some has a lot of energy and it can go right through all but the thickest of lead walls. So she noticed that there are these different types, alpha, beta, and gamma. She called them. But she didn't know what it was. So that came later. And it was later findings that led Ernest Rutherford to actually be able to probe the atom itself and discover what is inside an atom, which is kind of a big deal. So, the next step. Why does radiation even happen? And to get there, we need to understand the atom better. And about this time, right around 1900, 1904 or 5, a fellow named J.J. Thompson was studying high voltage electricity passing through vacuum tubes. So just think a blown glass bulb like this, and all the oxygen is vacuumed out of there and plugged, and he passes high voltage electricity through it. And it's called a Crookes tube. That was the first sort of implementation of it. And what happens is that something is emitted. There's a beam of something shooting straight out of the cathode. Now that's the negative terminal on the high voltage. It shoots straight out of the cathode and projects onto the other side of the glass. And the glass fluoresces. It glows green. So this is kind of weird. And if you place something, again, the Maltese cross, I guess just sort of a sentimental shape in science, it projects a shadow. So this thing in the way is blocking whatever the beam is. We still don't know what the beam is, but Thompson wanted to find out. And so he played with these Crookes tubes and cathode rays. And what he found was you can influence this beam with a magnet. You can influence it with electric current. And it depends on the polarity. So if you put a negative current on one side of the tube, it pushes all the beam down. So it actually deflects the beam away from the negative terminal. And vice versa. It attracts to a positive terminal. So from this, he quite rightly deduced that the beam has a negative charge. And so that's really all he could know about that. But it's important because this is in an atom we're talking. He's liberating this beam from an element. So if we're taking all these negatively charged particles from an atom, and we know that atoms don't have a net charge. There's no, if you do that same thing with atoms of gas or whatever, they don't deflect from magnetism or an electric current. So they have just the positives and minuses balance out. So if we're taking all these negatives out, there must be some positives in there to cancel them out and cause the atom of anything to not have a charge. So here we are around 1905. J.J. Thompson has got his plum pudding model of the atom. He's worked out that the electrons come out of an atom, or are a component of an atom, and therefore there must be some other positively charged particle in there, and he figures it's just like a plum pudding, negatively charged raisins in a positive plummy pudding matrix. So there you go. The next step was to test the plum pudding atomic model. Students of Rutherford, Geiger and Marsden, put a radioactive substance, like radium or uranium, I'm not sure what it was, but an alpha particle emitter, anyway, in a lead box so that the radioactive alpha particle emissions would be pretty much blocked, except they were allowed to escape through a small hole in the front of the box. In front of the box, an alpha emitter, was placed a sheet of metal foil, like gold or aluminum or silver. Behind the gold foil was a detector, wrapped almost all the way 360 degrees around it. And so the detector actually lights up when hit with an alpha particle. Remember, alpha particles are something that radioactive substances can emit. We haven't gone over what exactly they are yet, but we know that it's a particle emitted. Rutherford noticed and interpreted that, as expected, the particles shot right through the metal foil, just like you'd expect a bullet to shoot through a snowman. Only just very slightly changing angle, direction, and speed, as you'd expect a bullet to do through snow. The thing was, about 1 in 8,000 times the particle would hit something in the foil barrier and ricochet back or to the side, which is totally weird. And Rutherford remembers it like this. He said, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. On consideration, I realized that this scattering backward must be the result of a single collision, and when I made calculations, I saw that it was impossible to get anything of that order of magnitude unless you took a system in which the greater part of the mass of the atom was concentrated in a minute nucleus. It was then that I had the idea of an atom with a minute, massive center carrying a charge." Ernest Rutherford proved that the majority of an atom's mass is centered in an infinitesimal nucleus. And he guessed that it was probably positively charged because there are negatively charged electrons surrounding it. We now know that there's not only these positively charged particles in the nucleus, there are particles with a neutral charge as well, neutrons. Neutrons were discovered later, in around 1920, because Rutherford was looking at the discrepancy between where elements fit on the periodic table, so their number of protons, and the mass of an element. They didn't match up, and he could only reconcile the difference in mass and number of protons by inventing a neutrally charged particle in the atom's nucleus. So later on, in the 1930s, this was actually validated and neutrons were experimentally proven to exist. That experiment is a little more complicated and not so important to us, but again, an example of Rutherford making a pretty darn good guess.